Is it too disappointing to get like a free full credit on this, or is that good? That's okay with everyone? I don't. Yeah, just mix it up. All right, so course logistics. We are here. We're going to talk about heaps today a little bit. Big thing coming up, challenge 2 is due. How's everybody doing on challenge 2? Has anybody started yet? You have? Okay. Yeah. Anybody else? Problems, major concerns? Everybody's like scheduled a time with the TA? Okay. Cool. So that will be Friday, and then next week we will do exam review and exam 2, and then on Friday we'll start graphs. So that's programming challenge 2. Okay. So last time, if you remember, we talked about AVL trees, and the idea being that we have the binary search tree, but for it to be in a state where we get good guarantees on efficiency, we need to make sure that it's balanced so that it doesn't become like a long array, essentially, or a linked list. And we introduced this concept of rotations, this right rotation and left rotation, that we can do to subtrees in a tree in order to keep it balanced. So we were looking at making sure we didn't have something like this happen ever, and rather we have something like this. And we split that into 2 steps. So we said that kind of anytime we would insert something or remove something from that tree, we would check to see if it needs to be balanced. And that's kind of what we did on the quiz, was computing some of the things you would need to compute to check that. And then if it's out of balance, we'd use those rotations to fix the tree so that it is in a balanced state. And here's some of that math that goes along with that, which is pretty straightforward and is not too bad to code. And it turns out that AVL trees are pretty efficient. There are other types of balanced trees that let you have like more or less imbalance happen, but AVL trees are pretty good in terms of being like very strict, in terms of how unbalanced they can be, but also being efficient. And so there's an example of balancing a very simple tree with a left rotation. And we talked a little bit about the computational complexity related to this. And so if we have a balanced tree, in our case an AVL tree, that allows us to find an item in log n time, because essentially every time we do a comparison, we're kind of cutting our space in half here. And so that gives us log n, where n is the number of nodes. The same thing for inserting a node or balancing, doing the balancing as part of an insertion or deletion, because those are constant time, right? We're just changing some pointers around, and we kind of know how to do that. And it doesn't depend on the size of the tree. I mean, it depends on the size of the tree logarithmically. So log n is what we get.
When we say log n, we mean log base 2?
We do mean base 2 in this case, yeah. And that being just a factor of it dividing by 2 every time, yeah. It's a good question. Sometimes it's not always that, but.
We usually specify what the base is? Or writing log n?
Pretty much. I mean, in here you'll just have to do log in, and I mean honestly, pretty much every course that I've seen or taught, that's kind of just a go-to. We don't worry too much about that base. It matters more, I guess, like if you're in like a discrete class or something and you're proving these things, then you might care a little bit more about it. But it's kind of a small detail for us. And so then we said that we could build an AVL tree of n elements in time in log n. And the idea there being that each insertion takes log n, and we're going to do n of those insertions. And so you end up with the complexity of n log n. So today, I'd like to talk a little bit about heaps, which are a pretty clever data structure. It's really useful. There's not a lot to it. So we'll talk about kind of the very basics of it today, and then we'll do a little bit more, I guess, as in-depth as we can on Friday, but I think that you will like heaps. They are quite interesting. So the idea of a heap, and I should say that the word heap is used for many different things. So you will sometimes hear it in reference to like memory, things on the heap, things on the stack. In our case, what we're talking about is a binary heap. And so that is a distinction that matters, although it is the most common kind of heap that we talk about in data structures. And so the idea here is that if we have a tree like this, right, and it's a binary tree. Now, it's not a binary search tree, so that's important to remember. So don't think about doing the thing where you put the smaller one to the left and the bigger one to the right. We're not going to do that for this. But we are going to think about the structure of just a binary tree in general. And specifically, we want to think of what we would consider maybe sometimes it's called a nearly perfect or a full binary tree. And all that means is that for the tree, every level has to have all of the nodes except for the last level, which can have, maybe anywhere between all of the nodes for it and one node. So the idea being, if you were thinking left to right, the tree has to be full the whole way through. So that's something that's going to be a little bit different as we think about this in comparison to other binary trees. So when we've been doing like binary search trees, right, you could get things where you have like this going off in a zigzag over here, something like that. And so there would be more levels on one side or on one node. In this case, we're kind of constraining that. And we're going to just say, anytime we have this heap structure, and when we think of it as a tree, we're going to say that level 1 has one node, level 2 has two nodes, and kind of just keep carrying that through, and we'll never break away from that. And the reason that we do that is because we're going to store this in an array. We're not going to do this as a linked structure anymore. We're going to think about it both ways, but we're going to store it in an array, and that's going to give us some nice advantages. So there are two types of binary heap that we're going to talk about, a max heap and a min heap. There can be others, but these are the most common. And kind of, I guess what the go-to that you'll hear when people tell you about like a binary heap for the first time is they'll say priority queues. All right, so the idea being like you've got the queue, which we've looked at before, where somebody goes into the queue and it's like first in, first out, right? You're waiting in line for something, as you arrive. This can be applied to the concept of a line where, I don't know, maybe some people are more important than other people, and they're going to get to go ahead of the others. You can think of that in some glamorous settings, or you can think of it in some horrible settings, like an emergency room, right? Like you're going to triage, like whoever's bleeding the most gets to go first, even if they arrive last. So that is one of the most common kind of practical applications when we talk about heaps that you'll hear. But in reality, I think what is actually nice about heaps is that heaps, min heap, max heap, they are sorts. They sort data. And they sort the data in place, meaning you don't need any extra storage, and they do it quickly. And that's probably the best property of these data structures, is that you can actually sort a list of elements using them, and that is nicely called a heap sort. But it is kind of implicit in the structure, and you'll see that as we build it. So just remember, not a binary search tree, just a binary tree. Each level has to be fully populated before we go to a next level. And that last level may not be fully populated. And so sometimes called a perfect binary tree, sometimes called complete or almost complete. And here's the basic principle. the heap property. So we have a max heap property and a min heap property. And we treat these as distinct structures. So if we're doing a max heap, this is what has to be true. So for every node in our binary tree, the parent has to be bigger than all of its children. And that has to be true for every node we look at in the tree. For a min heap, it's just the opposite of that. The parent has to be less than all of its children. So what this means is that when this property is met and you have this structure, for the max heap, what will be the root node always? The biggest, yeah. And for the min heap, smallest, right? And so you can think about this a little bit and quickly realize if we can build these things in an efficient time and we can remove elements efficiently, if we wanted to sort something, we can just push everything into a heap and then pull the top element off over and over and over until it's empty, and then it will come out sorted. So because we arrange heaps in kind of a linear data structure as an array, you just have to do a little bit of mapping. When we tend to visualize it as this binary tree because that's very nice to look at. It's very easy to think about. But you can convert this into a one-dimensional array easily. And there are different ways to do it. I always use zero-indexed arrays. If you want to use start with a 1, then these formulas will change by 1. But if you are looking for the parent so if you're actually looking for a child, like let's say you have node 25, and you want to find its left child, then it's just a very basic formula where it's 2 times the index of what 25 is at plus 1, and that gives you the left child. The right child is just 2i plus 2, and if you were at a child and you want to find its parent, which you may not be able to see if you're in the back, all you have to do is the index of the child minus 1, divide that by 2, and always round it down, no matter what. And that will give you the index. And you can look at this and you can kind of read it out. So this is like the most basic example you can get right here. And it's just left to right and then top to bottom, and that's how we fill in the array. In code, it's very nice, really basic, one line, to map where things are relative to each other. So today we will look at a min heap for our examples. Just know that a max heap is exactly the same, just with the opposite comparison. And I think we'll look at a max heap on Friday, just for completeness. So when we think about building a heap, we start off with something, right? And so we can think of this a couple of different ways. So typically when we're doing a heap, we want to allocate a fixed amount of memory that we're going to occupy. And the reason is because we know that we're going to keep this tree full at every level. And so that does mean that if we don't predict how much we need or we need more, we would have to do a resize operation at some point. But that's not a major cost. And as we're doing these heap operations, we assume that we have the right amount of memory allocated. So there are 2 ways to construct the heap initially. Like if we have, say, this list of elements or items or nodes or whatever you want to call it, there are 2 different ways that we can go about initially constructing the heap. And when we talk about these nodes or elements, they are more formally called keys, with the idea being that they are a key probably pointing to a real object, a data object somewhere or something like that. So we're always comparing keys when we talk about this. You'll hear me and you'll see it called nodes or elements or whatever. But that is kind of the formal language for it is a key. And so there are 2 ways we can do this. we can either take our list of things we want to build into a heap and one at a time add them to the heap and maintain the heap property. Or we can kind of take them all at once and then do what's called heapify, official name, and convert that whole set into a heap. We will look at doing that on Friday. And the reason why we have these two approaches is that it turns out through some clever tricks, if we do it all at once, we can do it a little bit faster than if we do it one by one, although both are pretty fast. So let's talk about just doing them, adding them one at a time, because this is also something that you'll need, like if you have a heap that exists and you need to add more elements to it, this is what you'll have to do. So we always add to the end of the heap, and for us, the end of the heap is the lowest, or the furthest down level of the tree, all the way to the right. And we're going to add our new value as a leaf there. If that level's full, we can start a new level and put that at the beginning of it. So once we've done that, we've got our new leaf there, and we'll go through a visual example of this. Then we have to check our heap property and make sure that it's maintained. This is similar, like when we were doing like balance factors, like is the tree balanced here? So what we're checking in this case is, if we're in a min heap, we're checking to see is the parent of this new node less than the node? Because if it's not, then we're not a heap anymore. And we've got to change it. So in that case, this is just about a min heap. So if the new node is less than its parents, we'll just swap them. Then what we'll do is go to the parent where we've swapped our value and check with its parent. Kind of the same thing. We're just going to go all the way up until we don't actually have a problem. And because of the way the heap's structured, we don't have to worry about anything that's not in the ancestry line. So all the other parts are unaffected by what we're doing, which is nice. And so this is the basic principle for adding something. There are many names for this idea. You will hear trickle up, bubble up, heapify up. All of them just mean we are starting at the bottom where we added something, and we're going to work our way up as far as we need to maintain the heap property. Okay, so let's do an example here. So this is a min heap, and you can kind of verify that by looking at each node and see that its parent is in fact less than it for all of these nodes. And so this is kind of the visual, nice diagram version of this structure, and then how it would actually be stored in memory. This is just a zero indexed array, and you can see the values up there as well. And so that's how we would actually store it. And so, for example, let's say we want to add 63 to our heap. So remember, we always just add to the bottom level and all the way as far to the left as we can. So in this case, where will 63 go initially? Yes. So it will go down here. And then we've placed it there. So now we need to check to see if, for node 63, if this min heap property is satisfied. And so what we do is we take 63, we look at its parent 77. 77 is greater than 63. So is it satisfied? No, it's not. So we swap it, right? And you can see up here in the array view of this, all we're doing is just swapping these values around. And so we move it up here, and now we need to check its new parent, 67. And so checking that, is the heap property satisfied? No. So we just swap it again. And that's the theme as we go up here. And so then we'll check it with the root node in this case, 56, its parent. And is that satisfied?
Yep.
Yes, okay. And it's that simple. That is the whole game of inserting something into a heap. And if it were a max heap, we'd be doing the opposite comparison. So maybe a little more interesting is removing a single node from the heap, and in our case, a min heap. And so we're always going to remove the root, which sounds awful because, from other things we've done with trees, like removing the root is always going to cause the most chaos in terms of having to reorganize stuff. But it's not that bad here, and this is actually the advantage of the data structure, right? Is that we can always take the root element, and it will either be the min or the max, depending on what we're doing. But when we remove it, we do have to maintain that heap property still. So first what we will do, and there are different ways to think about this, so we'll approach it a couple of different ways, but we can think of removing that root value, and then what we're going to do is in its place, we're going to go down to the bottom of the tree to the rightmost lowest node that exists, kind of like the last one in the array, if you're looking at the array view. And we're going to put it as the root, no matter what. We're always going to do that. Then we will start to do a process where we work down to ensure that the heap property still is maintained. So you'll see this done different ways. So you can think of it like, say here that we're pulling 12 out, right? You can imagine it as taking 12 away and taking, the leaf at the bottom and putting it there. But what actually gives us a nice performance is that we actually swap them. Because what that does in the array representation is it puts that thing that we removed at the end of the array, and then we can just move the bounds of the array over. And so now our heap is smaller and our data is sorted outside of it. And that's how we can do this with no extra memory. So we kind of have our heap, like if we have like an array of elements, we come into it, we build our heap on top of it, and then we kind of shrink our heap away, and as it shrinks away, it's sorted. And so that's what makes this kind of a very nice structure and approach to things. Okay, but so when we remove this, whether we're thinking of actually removing it or we're thinking of swapping it, we have to make sure that we maintain that heap property. So now what we're going to do, since we've changed the root, right, we've swapped it, is we're going to start at the root and we're going to go down. And in the case of a min heap, we're going to look at the children of that node, and what we're looking for is the smallest of the two children. If it was a max heap, we'd be looking for the largest. And what we're going to do is if our node, in the case of the min heap, is bigger than one of these, bigger than the smallest child, okay, then we're going to swap it because that's what makes sense, right? We need to have the smaller values at the top. And then we're just going to repeat that down the tree just like we did up. And so as an example, it's going to be the same structure here. So let's imagine we remove 56. And so I'm going to put 56 over there, and you can see what I've done is I've taken 77 and just moved it up here. And I've not put 56 in the array, but we'll look at that representation of it later. So we pulled 56 out, 77 is now in its place, and now we need to make sure that we're maintaining this heap property. So we're going to look at the two children. We've got 63 and 89, so we want the smaller of the two. So looking at 63 and comparing these, so as this is this a min heap? No. So what we're going to do is we're going to swap with the smaller. Okay, so now we've got 63 up in our root, and we've got 77 where 63 was, and we'll do the same thing here. Is this good, or do we need to keep going? One more, yeah. So we'll make one more swap there. And now we can see, there's nothing else to compare against. So we now have satisfied the min heap property. We have a min heap still. And that is all there is to removing an element. And so you can see how both of these operations is log n time, right? Because we're just navigating the tree, binary tree, as we do these things. So a heap sort is nothing more than building that heap on a collection of data and then just removing. Depending on which direction you want to sort in, you can do a max or a min. And the benefit of it, again, is that you don't need any extra memory. You don't need any extra pointers. You're just computing the index of things and moving them around. And so that is kind of the powerful part of a heap itself, and a heap sort in particular, is that it is considered an in-place, is what you'll hear it called, is an in-place sort, meaning that you can have all the data there, and you don't need to have any temporary variables or have another, buffer of the same size or pull things out like that. You can literally just do this operation over the set of data, and you will get your sorted data back from there. So that's where I want to stop today. We'll do a little bit more on Friday. And yes, so do your programming challenges, and I will see you on Friday.